In today's demonstration, we're going to show you how you can use the Brillouin sensing system to measure changes in temperature and changes in strain simultaneously and independently of one another. You have to understand that our instrument measures changes in the Brillouin spectrum as light travels through the fiber. And the shift in the Brillouin spectrum is a function of both temperature and strain. So that in order to work out what either of those variables are, we need to be able to make two independent measurements. And to do that, we're going to use two fibers. One of them will be a different type of fiber than the other one, so its response to changes in temperature and strain will be different from the other fiber. So it will show a different shift in the Brillouin spectrum. By having two different Brillouin spectrums, we can solve for the two unknowns in temperature and strain. Let's go over what our setup is to demonstrate this. To begin with, we have our DSTS measurement system here. We have one fiber hooked up to one arm of the sensor, and it is our standard Corning SMS28 fiber. The other arm is hooked up to a different fiber made by a different manufacturer. So it will show a different response to the Brillouin spectrum than the Corning SMS28. Both fibers are running through this apparatus here, which we're going to use to change the temperature of the fibers and the strain imposed on the fibers. Here's how it works. Over here we have a clamp, and the clamp is on a movable stage that we can measure the position of using this caliper. The two fibers are clamped down and they run through this copper tube. The copper tube has heating elements running along it, and these heating elements heat up the copper tube. The copper tube in turn heats up the air inside, and the air inside warms the fiber. The fibers run through the entire length and come out the other side where they are held in place by a fixed clamp. They go through the fixed clamp and then are connected here together by a standard connector. So with this setup, we can change either the temperature or the strain on the fiber independently of one another, and be able to show what the temperature or the strain is imposed on the fiber. We'll be able to show in our experiment how we can change one or the other or both, and the DSTS unit will show you a measurement confirming that change in our system. Let's get to work. Okay, so as in all measurements made with the Brillouin sensing system, we start off by taking a baseline reading. We are trying to measure changes in the temperature and changes in the strain with the instrument. So let's begin. You start off clicking on the BOTDA function like you would for any other measurement. And we start off in our setup screen. Okay? Now we have a short length of fiber here. The total round trip path length is only 12 meters. So we're going to leave this short. We're going to leave this at 100 meters. This will give us some room before the fiber, some room after the fiber. Things will be well centered on the display so we can show you what's going on. The pulse width we're using is 5 nanoseconds, which is equivalent in terms of a spatial pulse of half a meter. And this is important because the section that we're heating up here is only 1 meter long. So we had to have a pulse width that's shorter than half the length that we're heating up and applying strain to, so you can actually see the changes and make a proper measurement from it. We're setting the spatial resolution, which is right here, the spatial steps at 0.05 meters. Now this is important because at some point we're going to have to set the position where one fiber is mated to the other fiber. We have to measure that very accurately. The DSTS system assumes that you start off with a fiber at the far point joined together, and that the two fibers run parallel along whatever you're making the measurements of. Okay? So it looks at the same distance from the splice point and assumes that's the same position in wherever you're making the measurement. So getting that position accurate is important. So we're using the highest spatial step size we've got, the finest one, 0.05 meters. It's as fine as we can go with the system. Other things, the fiber type, we're going to set that up when we go and take our baseline readings, because there are now two fibers that we have to deal with. Okay? We're going with our standard step size of 5 megahertz. And we're going to use again our fast general analysis, which will be fast enough that we can get readings in a reasonably short period of time, but is accurate enough to show the changes in temperature and strain that we'll be applying to this fiber. Again, by using the general analysis function, you can get even more accurate results, but they take more time to do the analysis. If I turn on the laser at this point, you can actually see on the screen right here a region of interest where the fiber strain is occurring. Okay? And there's basically two sort of bumps representing the two fibers. So things are working normally here right now. So since our setup seems to be good, let's take our baseline reading. So we go to simultaneous measurement, and we're using two fibers, so we're going to be using our dual fiber simultaneous measurement function. So make sure that that is clicked and hit OK. The screen you see here is pretty familiar. It looks a lot like the screen that we've always been using for measuring strain and temperature. We're going to make sure that baseline is activated. Okay? And we're going to make sure that our fibers are selected. Our first fiber, this one is labeled SIM AOC. This is our second fiber made by a different manufacturer, so it has a different response in this Brillouin spectrum. And down below, SMF28E. So these are the two fibers that we're using in our demonstration here today. Once they're selected, we hit the start button on the laser, and it now starts measuring the Brillouin spectra through both fibers. Okay? While it's recording, let's talk about a few points here. The fiber here right now is under tension. It is under strain. In order to make any sort of accurate measurement of temperature and strain, okay, the fiber always has to be under tension. Okay? As my physics professor used to say, there's a fourth law of physics: you cannot push on a rope. And the same thing is true with fibers. In order to measure strain, you have to have the fiber under tension. Okay? So it's being constantly stretched, and you're measuring how much it's being stretched. Okay? You're measuring that change in the strain of the fiber. Okay? Also, we are limited by the accuracy of our setup. The caliper here, okay, measures things to accurate about 0.01 meters. At least that's what the display shows. Okay? The length of fiber that we're stretching is just over 1 meter long. It's 101 centimeters from the tip of one clamp to the tip of the other clamp. Okay? So if I change this by 0.1 millimeters, it's equivalent to applying the strain of roughly 99 microstrain. Alright? We're also limited by how accurately this heats up the fiber. The display here is only showing 1-digit increments, and it will fluctuate up and down by a degree or so when it's in actual operation. It's also indirectly heating the fibers. The fibers are not in contact with the copper tube. We're relying on the tube to heat the air, to heat the fibers. So all that is happening in the unit. So right now it's finished taking the Brillouin spectrum. Okay? Initially we have the dead zone from inside the instrument. And then in here we actually have the transition going on. If I zoom in, okay, we have the transition going from fiber 1 to the point where they're joined to fiber 2. So the first thing we want to do in order to get this thing set up for making the measurements is setting the point where they transition. So if we go here and we zoom in some more, we can see one point here where it shows 6.08 meters and another point 6.13 meters. Somewhere in between is where we went from one fiber to the other. But this is where we have the limitation in our resolution, spatial resolution of the instrument. Okay? So we're going to type one of these numbers and put in. I'm going to put in the second number. So you type that number up here where it says connection point. So you type in the number and you're ready to actually make a measurement. Alright, so now that we've recorded our baseline reading, why don't we take a measurement without changing either the temperature or the strain? Simple enough. We make sure that strain and temperature is clicked, and we start the laser going, and it begins its measurements. Okay. While it's taking the measurements, let's talk about a few points here. In terms of our setup, there's about 1 meter of fiber here for the leads. Then we have the fiber loosely coiled here going through the loop, and on the other side of the loop there's about 1.5 meters off the fiber from each type before they're joined together. So the halfway point in the system, here in the tube, corresponds to about the 4-meter mark in our setup. Okay? So from this point here to the center of our copper tube is the 4-meter mark. What I hope to show you in this demonstration are the measurements at that point, and also show you that you can actually see the changes in the strain and in the temperature over that region of interest, where you can see the strain going up, leveling off, going back down again, and the temperature able to go up, leveling off, and go back down again. Okay. Once we show this, I'll demonstrate a change where we just change the strain and not the temperature. Then we'll change the strain and the temperature simultaneously. Do that a couple of times. Show a change where we change just the temperature and not change the strain. And finally we'll bring the strain back down again to show that we can come back to a similar reading again. So it's doing the analysis. So if we pick the 4-meter mark and zoom in on the strain, you can see that we have a flat curve here, both in terms of strain and in terms of temperature over the region of interest. Okay, so now let's change the strain on the fiber without changing the temperature. It's still at the setting that we originally had it on, which is heating it to just above room temperature. It's heating to about 30 degrees. Now we're going to adjust the strain. To do that, I loosen the locking nut and I push here slowly, while watching the readings here. And ever so gently it moves up. And I'm going to move it up to about 0.2 millimeters. And 0.2 millimeters corresponds to about 198 microstrain. But of course, the accuracy of the instrument, that could actually be 190, 0.19 millimeters, 0.21 millimeters. So this is the accuracy of the instrument itself. Alright, so now that we've adjusted the strain on the fiber, let's make a measurement. Same process as before. Make sure the strain and temperature is clicked on, and we start doing a scan. Okay? So, once more, the length of the fiber between the two blocks is 101 centimeters, and we've adjusted the stretch on the fiber by 0.2 millimeters. So the strain on the fiber is 198 microstrain. 200 microns divided by 1.01 meters gives you the 198 microstrain. Right now we're keeping the temperature constant. We haven't changed the temperature. So at the end of this set of measurements, we should be able to see the change in the strain, while at the same time the temperature of the fiber should remain relatively constant. We should be able to show you the start and end of the fiber as well. Okay, so you can see that it's making the strain measurements over the length that we're applying the strain to. Once we get through this measurement, we'll change the temperature and the strain together, and we'll be able to show how both of them have changed. Now when we change the temperature, it takes considerable time for the tube to warm the fiber up to temperature. Fortunately, you won't have to sit through the 10 minutes or so while we're waiting for the fiber to warm up, thanks to the magic of video. Almost done making the readings. We're about 10 seconds left in terms of making the measurements. It's gathered all the data, does the calculations quite quickly, and if we go again to our 4.03 meter mark that we're using as a reference, you can see that here we show the temperature as being quite constant, whereas the strain in the middle of our unit is just a little bit over 200 microstrain. It's showing 218 on the recording, which is pretty good. It's a good match in accuracy here. Over here, where the slope is rising up, about the halfway mark, that is where the 1 inch of the copper tube is. That's at 3.47 meters. And if we look over the other end, it's around 4.4 to 4.49 meters. So here is our 1 meter stretch that we're heating and cooling the fiber. And the reason why you're seeing the slope going up and the slope going down is, of course, because we're using a 5 nanosecond pulse, which means the resolution of the Brillouin detection system is about half a meter. And that's why you see the stretch going up and the stretch going down. But at the 50% marks, you can see it's showing you quite accurately that it's this 1 meter of fiber that's being heated and cooled. So, a good demonstration of it just measuring strain. Let's now go adjust the strain and the temperature. Alright, so let's adjust the strain again. We're going to go from 0.2 millimeters up to 0.4 millimeters. I'll back this off. There we go. Need a fine touch for this. There we go, 0.4 millimeters. And we'll increase the temperature here to 40. Okay? Now it's going to take a while for this to warm up, so we'll pause and we'll show you it once we have it up to the right temperature. So our instrument has settled down. It's showing 40 degrees C now for the temperature. We have 0.4 millimeters here for the amount that we stretched the fiber. So let's start our recording off. And we're off and running. Alright, it's down to the final few seconds of making the measurement. It's gathered all the data, 3, 2, 1, doing the analysis, and we have a curve. So it's showing for temperature, if we go to that 4 meter mark, 4.03, the temperature shifted by about 10 degrees, which is what we'd expect, given that we went from 30 degrees to 40 degrees. And the number for the strain in the center is reading 499 microstrain right now. A bit on the high side, but still within our expectations. And now that we've got that measurement out of the way, let's increase the strain on the fiber from 400 microstrain to 600 microstrain and see what recordings we get then. Okay, so we've now increased the strain from 0.4 millimeter reading on the dial to 0.6 millimeter reading on the dial, while keeping our temperature constant at 40 degrees Celsius. So let's start making this measurement. Okay, so this time we expect to see the temperature to stay relatively constant, but you'd see an increase in the strain. Okay, so we'll just wait for the recording for the measurement to be taken. Okay, it's finished taking the measurement, and if we take a look on our screen, temperature is showing now at 13 degrees here, and again, as before, there is some variation in the temperature of the copper pipe over time due to the limits of the accuracy of the unit here. Meanwhile, our strain here is reading right now 650 microstrain compared to our expected value of about 590 microstrain. So again, we're in fairly reasonable agreement here. So we're going to take some time now to increase the temperature by another 10 degrees while keeping the strain constant, and we'll see what the results are. Okay, so now we've let the unit warm up to 50 degrees Celsius. So now that's an increase of 20 degrees Celsius from our original setting. We've left the strain setting here at 0.6 millimeters, corresponding to somewhere around about 594 microstrain. So let's start off our measurement again. So we'll take these readings. So this will be able to demonstrate a situation where we've only increased the temperature but left the strain constant. So we can talk about this relative to our last set of measurements. Once we finish this measurement, we'll reduce the strain from 0.6 millimeter reading on our caliper down to 0.2 millimeter reading of the caliper, and take one more final reading to demonstrate the behavior of the unit. Okay, we just about finished making the measurements. It seems to just be doing the analysis. And let's see what we have here. So our strain is unchanged. It's still reading 645, almost exactly the same number as what we had before. Whereas the temperature is showing 20.97, a change of 21 degrees compared to what the instrument is saying of 20 degrees. So here we have a very good match, again showing that only the temperature reading has been noted, has occurred, and our instrument has measured it. Now for our final measurement, I've reduced the dial reading here from 0.6 millimeters corresponding to 600 microstrain down to 0.2 millimeters corresponding to just under 200 microstrain. So we'll take our last measurement here. So we start making our measurements, and in a few seconds we should be able to see the results. So we're down to our last 10 seconds of gathering the data. 2, 1, it's gathering, it's done, it's calculating now. And if we go again to our point, 4.03 meters, we now have a reading of 275 for the microstrain and a change of 21.4 for the temperature. So again, this is in rough agreement with what our settings are. So we're able to show that we can independently measure temperature and strain using a pair of fibers set up to make the measurements with the Brillouin DSTS measurement system. I hope you found this video informative. If you have any questions, please call us at OZ Optics and we'll be happy to help you. Thank you.